Hello guys, this is a short session on linear regression, and I'm Dr. Darren Edwards. So the very first thing you need to know about linear regression is what it is, what it's used for. So linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. Linear regression is a basic and commonly used type of predictive analysis. So a lot of people use linear regression to make predictions. One example could be stock markets. You could have on your x-axis is the axis that goes horizontally, could be time, and stock price could be your y-axis. So in that particular situation, you are trying to predict the price of stock based on the time, the amount of time, how many years that particular company's been on the stock market. So you'd hope it goes up. That's of course not always the case, but that's one example. Now, linear regression differs somewhat from correlation analysis in the sense that regression analysis is an attempt to determine causality. So how one factor, your predictor, predicts your DV, your outcome measure, your predicted. So how the impact of time has on your DV, which in the case I've just giving you, is your stock market price. So what does linear regression examine? Well, the overall idea of regression is to examine two things. I've already said it's a predictor variable. Does it do a good job in predicting a particular outcome variable? So it's a test, it's not necessarily, time is not necessarily going to be a good predictor for the stock market stock price. Some might be better predictors. So it's testing that. It's testing how good a predictor is at predicting a particular outcome variable. And secondly, which variables in particular are significant predictors of the outcome variable, and in what way do they indicate a magnitude and sign of beta estimates impact the outcome variable. All that means is you might not just have one predictor for a particular outcome, you might have several predictors, and I'll go through that in a minute, giving you several examples. And each predictor will have a beta estimate, and that beta estimate is the impact of that particular predictor on the outcome. So again, don't worry too much. I'm going to give you lots of examples on this. Now, the purpose of linear regression, social scientists are interested in using linear regression in order to discover the effects of one variable, e.g. height, on another variable, weight. So in this particular case, we're interested in whether height is a good predictor for weight. Your predictor is always your x variable, and your dv, what's being predicted, is always your y variable. So linear regression answers the question, how much will y change if x changes? So how much of the variance in y can be explained by the changes in x? That's how the textbooks would describe it. So in other words, if x changes by a certain amount, we were able to estimate how much y will change. So if we know by how much weight increases as a result of inches of height increase, then we're able to predict weight of the person from his or her height. We can use linear regression to suggest that a score on one variable influences a score on the other variable. So it's really how one variable impacts the other variable. This is why we say we can infer causal relationships, because we are directly looking at how one variable impacts the other variable, how your x impacts your y variable, how your x predicts your y variable. It's a causal relation. It's completely different to correlations, which are just simple associations. With correlations, you cannot infer causality. The two variables, x and y. The variable that is predicted is called the criterion or the dependent variable. So it's always on the y-axis. The variable is predicting the dv is the predictor. The IV variable, that's independent variable. IV is always independent variable. dv is your dependent variable. So your predictor is always on the x, and your criterion or your predicted is always on the y-axis, the vertical axis of your graph. Now, when you enter this into SPSS, you simply have two columns: your predictor variable here with a set of numbers, and your predicted in another column. Now you're going to have to excuse me, I've got various slides with different examples. This particular we're looking at marks. Can your mock exam mark predict your actual mock exam mark? So I'm going to throw in lots of different examples, and all you need to know is the fact that one variable is explaining or trying to predict another variable. Don't worry too much whether it's marks or height, trying to predict weight. That's somewhat irrelevant. The specific details of the examples are somewhat irrelevant, as long as you understand that numerically what we're trying to do is whatever your x variable is, we're trying to work out the change in your x variable and how it relates or how it predicts your y, the change in your y variable. So I hope that's clear. Now I'll explain the b, the slope. This is the amount by which y changes when x changes by 1, is known as your b, that's your slope. And I'll show you how that is described in the actual statistical outputs. So when you enter your SPSS raw data, you might have a variable such as age, a categorical variable such as gender, maybe income, and then maybe depression. Maybe you're looking at how age and income predict depression. And that will be an entirely feasible prediction analysis. So what you're interested in then would be, is income a good predictor for depression? Is age a good predictor for depression? And are they both together a good predictor for depression? That will be a multiple regression. So I'm going to show you both examples of a single predictor and a multiple regression where you've got multiple predictors. So you could have income in the first instance, looking at whether it predicts depression. You might want to add in something like age as a second variable to see whether that increases the power of the model. Okay, so the very first thing you want to do when you kind of analyze your data, you might want to just visualize your data in the form of a scatter plot. To do this, you just go to Graphs, Scatter, select Simple, and then enter Define, and then enter your whatever it is you're trying to predict. This could be your final exam scores, whereas your X, your predictor, is your mock exam. So in this particular situation, we would be looking at, does mock exam marks predict final exam marks? Or we could be looking at, for instance, does height predict weight? Whatever your particular question is. But in any instance, whatever your predictor variable is, that goes into the x-axis. The thing you're predicting, your dv, goes into your y-axis. So once you do that, you get a simple scatter plot. Usually if you double click the graph, you can basically add in a simple, it pops up the chart editor, and you can add in a line of best fit. Drop down menu typically appears. Now, depending on when you're watching this video, SPSS always changes. IBM SPSS always changes. That's the program we're using. It always changes to some degree over time, but usually it just requires having a look around, get the latest statistics book, latest SPSS book to find out where to find these things. But typically you double click on the graph and you'll see an option there, linear. So don't panic if some of your drop up boxes look a little bit different. It's just SPSS updating itself and trying to be more user friendly as time goes on. So you select linear, you select the line of best fits, and it will plot a line straight through your data as the line of best fit. So you can obviously see height there is a good predictor for weight. So the more we grow, typically the more we weigh. Now these are your unstandardized residuals. Basically we want these data points to be as close as possible to this predicting line. That will increase the confidence we have in our model. The further they are away from the line, the less confidence we have on the particular model. We basically want to increase the beta coefficient as much as we possibly can. So we want these data points as close as possible to the predicting line. So that was a positive relationship, by the way, and it was a positive relationship between those variables, and it means that taller people tend to weigh more. We know the relationship wasn't perfect. I showed you there was errors. If it was perfect, all those dots would be on the line. It's not. There's some error there. So that means some people who are tall may, for whatever reason, maybe they're very, very slender, not weigh very much. So it's not always the case that tall people, the taller you are, the more you weigh. Now, you might be interested, remember I said the multiple regression, you might be interested in another factor. So not just height, maybe something like metabolic function, for instance. So maybe as metabolic function increases, you weigh more. Or maybe that would be an inverse. If it was an inverse relation, maybe it'll go down this way. So an inverse relation would be maybe if you're processing nutrition faster than other people, maybe you're not absorbing the fats and all the proteins and everything. So maybe that actually is a negative relation going downwards. But it's good to explore a multitude of different predictors. That would be a multiple regression. And maybe the third predictor you want to look at could be something like calories per day. So maybe that as you increase the number of calories you eat in the day, your weight typically goes up. You can see the three predictor lines. We're going through the data points. Now, you can see there's a gap between the line and the data points. That's your unstandardized residuals, your error, your mark of error. And some lines, like this blue one, will fit better than the other lines. So this green one doesn't fit very well. This red one doesn't fit very well. So metabolic function and calories don't fit very well. But the best fit is the height. It goes through the most of the dots. It's accounting for most of the variance. So I hope you can see that in a visual graph. So the regression equation. When we perform a linear regression analysis, we obtain a regression equation which shows the way in which y changes as a result of x. From this formula, we can calculate someone's score on y from their score on x. The general formula looks like this: y equals bx plus a, or y equals a plus bx. The regression equation shows us that the way in which y changes as a result of x changing, the steeper the slope, the b, the more y changes as a result of x. So I'll show you how to identify those. So just remember, the b is the slope. That's basically how the gradient of the curve, and the a is a constant. And I'll show you how to find those in SPSS. So say the slope line is 10. This means that for every time x increases by 1 unit, y changes by 10. Regression also allows you to predict. The equation below shows that y is able to predict by multiplying a person's score on x by b and then adding the constant a. So it basically tells you how much exactly how much incrementally, by adding 1 unit increasing on the x value, what is the impact on the y value? So in example, a equals 0, starting point on the graph, is the constant, and b is 10, so the slope is 10. So this value 10 is known as b. Every time x increases by 1 unit, y increases by 10 units. So you can basically work out the impact of your x on your y by knowing what the slope and the constant is. So a simple activity would be, what is someone's predicted score on y when their score on x equals 20? Assume a, the constant is 5 and the slope is 2. Well, a very simpler formula would be 5 is your constant, your a, plus 2 times 20. Your score is 20. Remember, your slope is b, so it's bx. Bx is 2 times 20, because the b is the 2, and the x is the 20. So it's basically saying a is the 5, bx 2 times 20 equals 5, plus 40, because 2 times 20 is 40. 5 plus 40 equals 45. So the score on y, when the score on x is 20, is 45. So when x is 20, y is 45. And that's how you calculate the impact of x on y using the slope and constant. Mentioned errors in residuals. If we use our line of best fit to predict a person's scores, unless we have a perfect relation, we'll always have some errors. Data points are off the line represents the errors of prediction. So as I said, we've got the predictor line, and you've got your data points at a certain distance away from the predictor line. That marks your error of prediction. If we use our line of best fit to predict sales for each price, if we were doing a sales comparison, then we would obtain a predicted sales figure. The difference between actual scores and the predicted scores are called the residuals. So the predicted is the line, the actual is the dots around the line, and the distance between them, as I said before, are the residuals, the error residuals. When it comes to actually performing the linear regression analysis, you want to click on Analyze, Regression, Linear, move the criterion variable into the dependent box and the predictor variable to the independent box, and click OK. So your dependent variable goes into this box here, just click that button there. Your independent measure goes into this particular box, click that into there. Use the enter method, and here you have it. Your dependent goes in there, your independent goes in there, and you're using the enter model. You want to perhaps click on the options, and you want to click the model fits. It's always good to have the confidence intervals and some estimates. So click those if you can. When you press OK, the very first table is going to come up is going to be this. We're looking at the adjusted R squared. This is the effect size of our overall predictor. So 0.932, that's very, very, very good. You want that to be as high as possible, close as possible to 1. So we're very, very confident in the amount of variance. So SPSS provides you the square of the correlation coefficient. This on the output was 0.39, so your adjusted R squared was 0.37. So we can say 94% of the variation in weight can be explained by the variation in height, for example. So you can make an exact description in terms of how much variation in one variable accounts for another variable simply by using your adjusted R squared. Standard error, again I mentioned error. Remember, our statistics are not free from error. We analyze the results with a particular sample, and it may be that sample on another day would give us slightly different results. With repeated measures, we would find a range of different values. The standardized deviations of such distributions are called our standard errors. The standard error gives us a measure of how accurate our estimation is likely to be. Standard errors are estimated, and just be aware you have particular errors and standard errors in your analysis. Now, the second box that will appear in your output results will be your ANOVA model scores. This is your model, your overall model significance, your F value, there's your degrees of freedom. The summary table shows you whether your regression line is significantly different from zero, i.e. predicts better than would be expected by chance. Remember, if the slope equals b, then the line of the best fit is horizontal. In this case, f equals 194.1 with an associated probability of 0.01. We can just say we can reduce that to 0.001. It's probably another couple of zeros then a figure, but we can reduce it down to 0.001. This means that the result is highly unlikely to have risen by sampling error. And then we have our beta coefficients and the significance of it. So it tells us the strength of the actual predictor, and that is very, very strong. So B slope, as you can see, the value of B is 12.39. This means that for every pence, remember your B is your slope, that means for every pence rise in the price, sales will drop by 12.39. Remember at the B value was your beta was a negative value, so it indicates an inverse relation between the two variables. While a standardized error could be used as a measure of error prediction, SPSS gives us the confidence limits which are based on the standardized error. The confidence limits show us that 95%, we're 90% confident that our population slope can be found within the intervals of minus 14.31 and minus 10.4a. So we would have seen on that previous graph the previous output, the confidence intervals shown. So this is fairly narrow, and we're fairly confident of our findings. The slope B has been converted into a standardized beta score at the end. The value was minus 0.97. This means that for every one standard deviation increase in price, sales figures decrease by almost one standard deviation. The intercept A, the value of the intercept is also given along with the standardized error. In the inputs given by SPS, the value of A is given in the row label constants, and you can see that. Confidence limits are also given. The values of A and B allow us to state the regression equation. So we need to understand what's our constant, our A, what's our B, our slope. In order to do that, the calculation, the algebraic calculation to find out the impact of X on Y. So if you remember, we did that exercise earlier. So we translate, in this particular situation, we translate the algebraic formula of y equals bx plus a into a specific formula using the following, y being sales. So in this particular situation, we're interested in terms of whether the price of Diet Coke, for instance, affects the sales of Diet Coke. So if our A on our outputs is 1513.96 and our slope, our B, is minus 12.39, we can put that into the equation and calculate the effect of your X on your Y. So when you report the outcomes, you'd say something like linear regression was carried out to determine the effect of price change on sales of Burper Coke. It was found that for every 1 pence increase in price, sales decreased by 12.39. Also, the adjusted R squared was 0.932, suggesting that 93% of the variance of sales of Burberco can be explained by the variation in price. Confidence limits demonstrated that we are 95% confident that the predicted slope is between the intervals of minus 14.31 and minus 10.47. This shows that we are 95% confident the result F113, or degrees of freedom, equals 194.16 and a probability of 0.01. All of that, so you get that in the model outcome, the very first table, the very first output I showed you, is accurate between those intervals. So that's how you report it. So all that information would have been in those outputs I just showed you. One separate small deviation, if you did have wanted to do like a multiple regression, you would just add in more than one independence. In this situation, we've got two independent variables to predict our outcome measure. Everything else is exactly the same. We've just inputted two predictors. We select the options or the statistics button and click the estimates, model fit descriptors, and the collinearity diagnostics is very, very important in terms of identifying any potential multi-collinearity. That's where our predictors are overly correlated with one another. And then press continue. You get a table such as this, where you've got your particular outcomes, and you've got your age, reading, age in months, standardized reading scores, standardized spelling scores, for instance, and they basically correlate. You basically do a correlation with all the other variables to see how each one correlates. You'll see a 1 there. All that basically means is percent correct spelling, and it's also got the same variable, so it's correlating with itself. So you'll have one which is perfectly correlated. That's absolutely fine. The rest then are basically just trying to identify whether any of these are too large. That's quite so standardized spelling scores is very, very similar to percent correct spelling, but that's our DV, and so the rest of them seem okay. So just be aware that you have to do a multi-collinearity test before. The standardized beta coefficient. So once you've pressed OK, I haven't shown you all the F value tables and the R squared and all the rest of it, simply because I just showed you that with the linear regression, the simple one predictor variable. This is where we've got more than one predictor variable. So the important thing here is your beta, your standardized coefficients. Each one is coming out with a beta score. And as you can see, your standardized beta, 0.786, is higher than the others. So your standardized spelling score is the most powerful predictor you have. It's more powerful than your standardized reading scores and your reading aging months and your aging months to predict the percent correct spelling outcome, your DV, your criterion outcome measure. So that it just tells you which of your predictors are the strongest in terms of accounting for the change in variance of your y being accounted by your x variable, which in this particular case the greatest variance accounted is the standardized spelling score. Okay, so the standardized beta coefficient gives us a measure of the contribution of each variable in the model. A large value indicates that a unit change in this predictor variable has a large effect on the criterion variable. The t and the sig p values give a rough indication of the impact of each predictor variable. A big absolute t value and a small p value suggest that a predictor variable is having a large impact on the criterion variable. If you requested collinear diagnostics, these will be also included in the table. So in terms of the write-up for this, when you're reporting the results of a multiple regression analysis, so I've just done the single regression, the linear regression. This is now with multiple predictors. When reporting these outcomes, you want to inform the reader about the proportion of the variance accounted for by your model, the significance of your model and the significance of your predictors. So those three things are very, very important. In the results section, we want to write using the enter method, and there's lots of different methods I haven't covered, like the backwards method. There's also a hierarchical regression method. Now, we're not going to look at those in this particular session. I might do some further sessions, and I'm also going to do a session where I go through it with you on SPSS, so you can see what to press. But this is how you report it for now. Using the enter method, a significant model of f 442 equals this particular figure, and p is very, very small. So it's a significant finding. The overall model is significant. Again, you get these outcomes from the tables that are outputted. I didn't show you it for the multiple regression just because I showed it for the linear, the single predictor. The adjusted R squared in this case was 0.83, and those are your beta outcomes. I just showed you the table with that. So you need to report each of your beta outcomes and the probability associated with each of those beta outcomes. Okay, guys, I hope you enjoyed that. Don't worry if that was a little bit too fast. I'm going to provide some more supportive documents if you're one of my students online, and also I'll do some follow-up videos in terms of showing you kind of like a tutorial by hand. So stay tuned for that. I hope you enjoyed.